This next lesson in our probability chapter, we're getting into probabilities involving and. You may remember that a couple of lessons ago, we talked about probabilities involving or, and that was always addition. We were always taking two probabilities and adding them together to find a combined probability. Now we're finding the probability of two things happening at the same time. So essentially the intersection. And what I really want you to take away from this statement right here, and I'm not sure if you need to copy this in your notes or not, but is that when we're dealing with intersections, which are and situations, remember that's what that means, that really what we're doing is multiplying probabilities together. We're doing the probability of the first event times the probability of the second event. Now, this second statement may look a little different than what you're used to. So this says the probability of A times the probability of B given A. That's what this symbol means. So off to the side here, I'm going to kind of jot that down. That this is what's called conditional probability. And we're going to talk more about that as the lesson goes on. Conditional probability. Okay. And so what that means is basically we're taking the probability of B happening, assuming that A has already occurred. Okay. And sometimes the fact that whatever event A is, sometimes the fact that event A has happened doesn't change the probability of B happening. Sometimes it does. So if it does change the probability, we just have to take that into consideration. Okay. But again, really what this statement is trying to say is that if you're trying to find the probability of two things happening at the same time, you're multiplying probabilities together. You just have to consider the fact that the first event has already occurred when you go to take the probability of the second. And I think you'll understand what I mean by that when we do this first example. So these are all dealing with decks of cards. You could refer to the card sheet that's on the back of your dice sheet if you're unsure about how many different cards are in a deck and things like that, if any of this is confusing to you. So this first one says, what's the probability of drawing a jack and then a red card with replacement? Now that with replacement piece is going to factor into this idea here. So we'll talk about that in just a second. Let's start with just what's the probability of drawing a jack? And I'm not going to do this for every problem, but the probability of drawing a jack is, let's see, there's four jacks in a deck, so that'd be 4 out of 52. Now, normally what I would say here is we have to find the probability of drawing a red card, assuming that I've already pulled out a jack. But the fact that I'm using this with replacement means even after I pull out that jack, I'm going to put it right back in the deck, and that kind of resets everything. So I don't have to worry about changing the probability of this second event. The probability of getting a red card would be half the deck. So that's 26 out of 52. So to find this probability, I'm going to take 4 out of 52, which by the way reduces to 1 out of 13. I'm going to do that just to save myself some mental math here. And then the probability of a red card is 1/2, 1 out of 2. And that would be 1 out of 26 as my final probability here. Okay. So now this next one is without replacement, and I think you'll see what I mean, that's going to affect some things in this problem. So let's start with just the probability of drawing a queen. Really, that's going to be the same as the probability of drawing a jack. There's 4 queens in a deck, so that's 4 out of 52. And then a 7 without replacement. Okay, so there's 4 7s in the deck, but without replacement means that I'm assuming that I already drew a queen and left that out. Okay, I didn't put it back. So what that really changes is the fact that now there's not 52 cards to draw from, there's 51 cards to draw from. And let's see, I did not prepare myself with a calculator here. Here we go. I guess I could have reduced that fraction a little bit. Let's see, 4 out of 52 is 1 out of 13. So that's going to work out to be 4 out of whatever 13 times 51 is, 663. And yeah, that's not going to reduce because that can't divide by 4. So that's my probability, 4 out of 663. Okay, so now this next one, and again, this is without replacement. So when I go to find the probability of my second event, I have to do it as though this already occurred. So a 9 of spades, that's one specific card in the deck. There's only one of those. So the probability of that happening would be 1 out of 52. Now, when I go to find this probability, I'm assuming that I already took out that 9 of spades and it's without replacement, so I didn't put it back. So what's the probability of drawing another spade? Well, normally there's 13 spades in the deck, but I already took out the 9, okay? So now I have 12 spades left in the deck. And because I took out a card and didn't replace it, I'm back to having 51 cards instead of 52. So that's what this is talking about. The probability of B given A means you're finding the probability assuming that that first event occurred already. All right, so that's going to be, let's see, 12 out of, these denominators get crazy really fast, 2652. That does reduce some, I'm sure. Yep, so that's 1 out of 221. Okay. Drawing a red card and then another red card with replacement. Okay, so drawing a red card is 26 out of 52, which is 1/2. And I'm multiplying by another red card, assuming that I pulled a red card out, but with replacement means I went ahead and put it back in. Okay, so I'm back to the original deck, and so my second probability would still just be 1/2, and I would say this overall probability is 1/4. So you'll notice that like in this example and this example that were with replacement, when I went to find that second probability, because I replaced the card, I really reset everything, and my probability of that second event didn't change based on the first event. That's what's called being independent. So this definition here, and if you need to pause the video to get the definition down, you may, but two events where one thing happening does not affect the outcome of the other, that's what's called being independent, okay? The mathematical definition of being independent is shown here. So events are independent if and only if, and you will notice that this statement is really very similar to this one we started with. The difference really is here, okay? The difference here is that this is not a conditional probability. This is just the probability of B. Here's what this is really saying, and I kind of wish they would word it this way. If two things are independent, then the probability of B given A is the same as probability of B, okay, by itself. So if the probability doesn't change when I throw this event A into the mix, if it still just stays the same probability that it was originally, that's when two things are independent. That's why this works, because I can basically just take that probability and swap it with that probability of B. I also want to point out that this statement is an if and only if, because you're going to be using this statement in both directions. So sometimes I'm going to tell you that two events are independent. And if I tell you that they're independent, then you know that you can multiply the probabilities together. Okay? Now, technically, you can always multiply the probabilities together. It's just that if they're not independent, you have to use conditional probability, which is like what we did here and here when we changed those probabilities slightly. Okay? The other way we're going to use this statement is we're going to say, if I multiply two probabilities together, and it comes out equal to the probability of the intersection, which actually should have been at the end of that statement, and it comes out equal to this, then I can say for sure that the events are independent. That's going to be the critical one, because here's what's going to happen. I'm going to give you events and I'm going to say, are these two things independent? And what tends to happen is we try to think about them logically. We try to think about them practically. And we say, would that thing happening affect the outcome of this thing? And we try to reason our way through it. That doesn't work in math. It's not a matter of being able to justify with words. It's a matter of being able to justify mathematically. So for you to be able to tell me for sure whether two things are independent, this right here is what you have to show. You have to show me that this is true. Okay, so we're going to do some examples in just a minute where that's exactly what we're going to do. Is we're going to find this probability, we're going to find this probability, and we're going to find this probability, just all on their own. And then we're going to multiply these two together and check and see if it works out with this. Okay, and if it does, if these two things are actually equal, then we say, yes, it's independent. If they're not actually equal, we say they're not independent, even if it seems like they should be. Okay, so we might get into that a little bit in this next example. So, coach keeps records on the basketball team. When a player shoots 2 free throws, 65% of the time they make the first shot, 70% of the time they make the second shot. And I want to know, are these two things independent or not? Well, this is one of those situations where we would look at this and say, well, making the first shot shouldn't have any effect on whether they make the second shot, right? I mean, it shouldn't happen logically, but we need to be able to say so mathematically. So what I would really need to know, this is probability of A. Let me do this in this color here. This is probability of the first event happening. This is the probability of the second event happening. What I need to know is the probability of both events happening, because then I can use this formula to check. So what I need to know is the probability that a player makes both shots, because that's the intersection here. So in all of my record keeping, I could go through and count up how many times did a player make both shots. If that happened to be, and let's see, what were these two percentages, 65% and 70%? So if I found that 45.5% of the time my basketball players were making both shots, I could conclude that the first shot and the second shot don't affect each other. But if I found anything other than that number, if I found something other than 45.5%, that means that one of the attempts is affecting the other. Maybe if you miss the first shot, you're more likely to make the second because you can learn from your mistakes. Or maybe if you miss the first shot, you're more likely to miss the second because now you're nervous and flustered. So we don't know what's actually happening here. But mathematically, this is the relationship we would need to see to be able to determine if these two things are independent or not. Okay. So we're going to get into that here. And I think this is working, well, some of these are working with dice. I don't have a dice sheet handy, so we'll just kind of talk through it. You could be referring to your dice sheet if you want. So we're going to roll a fair die twice, which is essentially what your dice sheet is showing. And I want to know what's the probability of these two things happening at the same time. I take that back. That's not actually what I need to know. I need to know if these two things are independent. So does rolling an even number on the first roll have an effect on the probability of rolling a number larger than 4 on your second roll? I wouldn't think so, right? Because this is one die and this is another. The two dice should be like independent from each other. They're not affecting each other. But here's how we're going to find out. We're going to find the probability of A. Okay. And the probability of rolling an even number on the first roll would be 3 out of 6, which is 1/2. And then we're going to say, what's the probability of rolling a 4 on the second die? So probability of rolling a 4, or sorry, greater than 4 would be 5 or 6. So that would be 2 out of 6, which is 1/3. Then what I want to do is find what's the probability of both things happening at the same time. And to find that, what I'm really going to use here, and I'm going to just kind of pretend, but This is where I'm going to use a dice sheet to count these up. So I am looking for, out of 36, because there's 36 outcomes from rolling 2 die, how many of them have this happening, where I have an even number on the first roll and a number greater than 4 on the second? And just off to the side, okay, so an even number on the first roll would be a 2, a 4, or a 6. There's a reason I'm writing them twice. A number greater than 4 on your second roll, we said that could be a 5 or a 6. So that would be like a 5 or a 6, 5 or a 6, 5 or a 6. So these are the combinations from your dice sheet. So we could have 2, 5, 2, 6, 4, 5, 4, 6, 6, 5, 6, 6. That would fit the intersection. That looks like 6 outcomes out of 36, which is 1/6. Okay, so what does all of this mean? What we want to check is it true that this probability times this probability equals this probability? And yes, that is true, right? 1/2 times 1/3 is 1/6. So that checks, and we would say these two things are independent. But notice that I had to justify that mathematically. I can't justify that by just saying, well, when you roll one die, that doesn't affect how you roll the other die. I mean, that makes sense to us in our head, but we have to really make sure that we can justify mathematically. Okay, so flipping a fair coin 4 times, and we want to think about flipping all heads versus flipping all tails. Okay, so flipping a coin 4 times, just real quick, if I go back to my counting principle, there's going to be 2 times 2 times 2 times 2, which is 16 different possibilities. Okay, so every time I flip a coin 4 times, there's 16 different ways that could come out, because there's 2 choices for the first coin, 2 choices for the second coin, and so on. So these probabilities are going to be out of 16. So the probability of getting all heads would be one of those 16 possibilities. If I was to make a list of all of the different ways I could flip 4 coins, or flip a coin 4 times, one of those out of the 16 would be all heads. Another one of those would be all tails. Okay, so now the intersection is always the tricky part. Out of those 16, how many of those combinations would have all heads and all tails at the same time? Think on that for a second. I'll say it again. Out of those 16 possibilities, how many of them would be 4 heads and 4 tails at the same time? If you're confused by that, it's probably because it's a big fat 0. These two things can't happen at the same time. Okay, these two things are mutually exclusive. It's not possible for me to have 4 heads and 4 tails at the same time. A lot of people mix up mutually exclusive with independent. They feel like those two things should kind of be connected. They are, but not in the way that you would think. When two things are mutually exclusive, they can't be independent, because if I know for sure that A happened, then B can't happen. And so that's a dependent event, because this probability changed as soon as I said I knew that A happened. Okay, so our check here, I'm kind of getting ahead of myself here, but what I'm really looking for is it true that 1 out of 16 times 1 out of 16 equals 0? Okay, that's a big fat no. So these events are dependent. Okay, opposite of independent there. Okay, they are not independent, because the probability of A times the probability of B does not equal the intersection. Okay, so same thing here. Rolling a pair of dice. The first die shows a 3. Okay, so the probability of rolling one die and having it show a 3 would be 1 out of 6. The probability that the sum of the dice is 9 Well, then I have to think about my dice sheet. How many different ways can I make 9? So off to the side here, I can't make it with a 1. I can't make it with a 2. I could do it with a 3 and a 6, a 4 and a 5, a 5 and a 4, or a 6 and a 3. Okay, so there's 4 ways to get a sum of 9 out of 36 options. Okay, 4 out of 36 is 1/9. And then I want to think about what's the probability of both happening at the same time. Well, if I know for sure the first die is a 3, there's really only one way for both of these things to occur. This intersection is this possibility right here, which is 1 out of 36. Okay, so what I'm checking here is 1/6 times 1/9 equal to 1 out of 36? And again, that is a big fat no. These are dependent events. Okay? Because as soon as I lock in the fact that the first die is a 3, that changes my probability here. We said this probability was 4 out of 36 because this could happen 4 different ways. But as soon as I lock in event A, this is now the only option I have. I get rid of these other options because event A has to occur. So that's why this is a dependent event, because the probability of this happening changes based on whether or not event A occurred. Okay, so another rolling pair of dice one. The first die shows a 3 and the sum of the dice is a 7. This one is interesting. I want you to look at this one compared to this one. Really, they look similar, right? I mean, the only difference is we're doing a sum of 9 or a sum of 7 now instead of a sum of 9. So again, that common sense piece of you might want to say, well, of course it's going to be dependent. We just did this. Let's check it out. So the probability that the first die shows a 3 is 1/6. Again, because there's a 1 out of 6 chance of getting a 3. The probability of getting a 7, well, let's see how many different ways can we make a 7? 1/6, 2 and 5, 3 and 4, 4 and 3, 5 and 2, 6 and 1. Okay, so I see 6 out of 36 ways, which is equal to 1 over 6. And the probability of both happening at the same time would be, when does the first die show a 3 and the sum of it is a 7? So that would be this possibility here, which is, again, 1 out of 36, just like it was before. But look at these numbers now. When I go to check this, 1 out of 6 times 1 out of 6 is 1 out of 36. That does check out. These events are independent. Okay? Kind of weird, right? The reason that's weird like that is that sum of 7 on a dice sheet is kind of a unique thing. The sum of the 7 is the only number that you can get no matter what you roll on the first die. So for example, if I'm trying to get a 9 and I roll my first die and it's a 2, I automatically know that a 9 is impossible, right? The 7 is the only number that you can get no matter what comes out on your first die. It's the only one where all 6 of these are possibilities, okay? And that leads to independence where there's not typically independence. So the only way to know for sure is to do this math and check it out, okay? By the way, this is bugging me. I should cross these off. These are not equal to each other. Okay, so we technically already talked about conditional probability, but now we're going to actually do some problems that involve it. So conditional probability, that's this thing that we talked about at the beginning. Okay, the likelihood of an event occurring given that another event has already occurred. Okay, but what we're going to do now is we're going to kind of restructure our formula that we had a minute ago so that we have a formula for calculating conditional probability. If I'm asking you, what is the probability of this happening, assuming that this already happened, we want a way to be able to figure that out. So here's what I'm going to do. I'm going to take that formula that we started with. We started with probability of the intersection is probability of A times the probability of B given A. And we want a formula that has this thing by itself, which is right here. So what I'm going to do is I'm going to divide this side by probability of A. I'm basically going to take this probability of A and just move it to the other side. And so to do that, I'm going to divide because this is multiplication. And so I can say the conditional probability of B is the probability of the intersection divided by the probability of A occurring. Okay, so this formula in purple, I don't like the way those kind of got stacked together here, but that formula is going to be important for you to know. It's really just a restructuring of this one, so it's not a formula that you should have to memorize, but probability of B given A is probability of the intersection divided by probability of A. So let's look at this example 4. We surveyed the JHS student body, found that 54% of students drive themselves to school and are involved in extracurriculars. 72% are involved in extracurriculars. So if I select a student that drives themselves to school, or what is the probability that I select a student that drives themselves to school if I'm only choosing from students who are involved in extracurriculars? Okay, so I'm not asking for what's the probability that just any student at JHS drives himself to school. I'm limiting my scope to just the students involved in extracurriculars. So let's see if we can label these things. This is, we've got drive themselves to school and involved in extracurriculars. So this here is the intersection. Okay. This, the extracurriculars, we're going to call that event A. So this is the probability of A right here. Okay. The 72% is probability of A. The 54% is the probability of the intersection. And see this wording here? We want the probability that this thing is occurring given that they are involved in extracurricular activities, given that this is occurring. So the question is asking for what's the probability of B happening, driving themselves to school, given that A has already occurred, given that they are involved in extracurriculars. So this is the thing we're trying to find. This is the formula we're setting up here. And I think once I get the formula set up, the numbers will make sense to you. So the probability of B given A, which is what the question's asking for, probability that a student drives themselves to school given that they're involved in extracurriculars, is the probability of both, which is the 54%, I'm going to put that as 0.54, over the probability of just being involved in extracurriculars, which is the 72%. Here's why that should make sense to you. The probability of them driving themselves to school here is 54%, but it's not 54% out of 100%. This is 54% out of this group that drive themselves to school already. So 54% out of 72%, that's what this setup looks like. And so I'm going to just divide these two, 0.54 divided by 0.72, and I end up with a 75%. So if I restrict my student body to only the students who are involved in extracurriculars, and I say, all right, how many of you drive yourselves to school? 75% of them would answer yes to that. So these ones are a little bit tricky, but if you can go through and label what the different numbers and values are and figure out what it is that you're trying to solve for with that conditional probability, it usually just ends up being a division problem. I'm just dividing these two numbers. It's just a matter of getting it set up correctly. Okay, this is a tricky lesson. So take some time on the homework tonight, really put some thought into it. We will definitely spend some time talking about this in class before our next quiz.